Okay. So, hello everybody. Thank you for coming for our third lecture today. Today we're going to talk about probability. It will be the last lecture that really deals with the theoretical part. From next week on, we will deal with the more applied parts of machine learning. So don't worry, the foundational part that is a little bit more abstract and less practical will soon be over. But today is a very important lecture because it gives you a general idea of how you can infer something from an observation that is subject to randomness. And it also gives you a different view on the optimization problems that we have to solve when we do machine learning. So you might remember when you think back to the linear regression that we just said, okay, let's minimize the squared distance between the observation and our prediction. And this is kind of a little bit random, or might seem a little bit random, but you can motivate it from a stochastic point of view. And today's lecture will give you an understanding of that. So let's start with the basics. What are things like probability and what are the terms that we're going to use? The first thing is the probability of a set A. So we call the probability of A, where A is a kind of a special subset of the superset omega, the size of A. So why do we pick such a definition? So you can think about it like that. We have this big rectangle, which is our superset omega. We assume that the size of omega is equal to 1 because, as you know, all the probabilities, all the possibilities have to sum up to 1. And our set A is somewhere in here. And we now randomly throw darts into omega. And intuitively, the probability of hitting A, of throwing a dart into A, is equal to the size of A in omega, right? So one thing, I said it has to be a special subset. For our purposes, you can just think of it as the size of the subset, but to make it really theoretically sound, you need to have a little bit more specific definitions for that. And if you're interested in that, I can suggest to you to look at basically any book on the axiomatic foundations of probability, and it will give you a better insight into that. But for our purposes, this will be enough for you to know. So having defined the probability, we can define the conditional probability, P of A given B. And we define the conditional probability as the probability of A intersected with B divided by the probability of B. So when we have another set, this was A, and we have another set in here, B, then this here is A intersected with B. And basically we want to know how likely is it that we hit A if we already know that the dart landed somewhere inside of B. And we say A and B are stochastic independent. Exactly if P of A and B P of A intersected with B is equal to P of A times P of B. So to relate that with the conditional probability, basically it means P of A given B is just equal to P of A. So knowing that if A and B are stochastic independent, knowing that we already hit B does not give us any additional information, whether or not we also hit A. And with these things, we can introduce our first theorem, the Bayes theorem. And Bayes' theorem tells us the following. P of A given B is equal to P of B given A times P of A divided by the probability of B. The proof is quite simple, actually, because we know A intersected with B is the same thing as B intersected with A. So we know P of A intersected with B is P of B intersected with A. And now we just plug in our definitions. And by dividing by P of B, we immediately get the theorem. So what does it mean? Like basically, it means we can trade the probability, the conditional probability A of A given B with the conditional probability of B given A. So when it's easier for you, or when it's more suitable for us to know P of B given A than to know that conditional probability, then we can just switch them. However, it comes at a cost. We also need to know P of A and P of B. Nee, lass laufen. Nur falls es jetzt ein Problem gibt, können wir hier schneiden. So now we're going to introduce the next concept, the random variable. So we call capital X as a random variable if it takes an element from omega and maps it to the real numbers, and it is an integrable function. And we can then say the probability of capital X being smaller or equal than y is defined as the probability of the set omega, small omega in our set omega, where x of omega smaller or equal than y. So basically, now we have way more general concept of probabilities. We can now talk in terms of numbers or in terms of a variable, and we can relate it to our random dart throwing with that little trick. So when we now have a little bit more complicated versions of randomness than throwing a dart, with that setup, we can relate it back to the dart throwing interpretation. And a random variable also has a cumulative distribution function and the cumulative distribution function maps from R into the interval 0 to 1, and it maps the real number t to the probability it maps the real number t to the probability that our random variable is smaller or equal than t. So basically it already tells you when you increase t, the cumulative distribution function has to grow, so it has to be monotonic, because, well, the probability that it's smaller can not decrease, because basically you already take or the values where your function is, let's say, smaller or equal than 1, is a subset of all the points where your function is smaller or equal than 2. So we know that the cumulative distribution function somehow has to look like that. So let's say we have this is our t, and this is the CDF of x at t. Then it cannot be bigger than 1, right? The biggest probability we can have is 1. So there's one asymptote here. And when we go further and further to the left, our distribution function will get arbitrarily small, right? So because we exclude more and more and more omega from our set. So basically we have something that must look like that, must be monotonic, and it will have two limits here. If the cumulative distribution function can be differentiated, which is mostly the case, or for many practical random variables or random variables of practical interest, that is the case, we can also define the probability density function. So x is a random variable, and the cumulative distribution function of x is differentiable, then the differential with respect to t is called the probability density function, the PDF. We can also define the expectation So x is again our random variable. And g is an integrable function. Then the expectation of g of x is defined as the integral over all of r g of t times the probability density function of x at t to delta t. So a few things to note. First of all, the expectation is a linear function. And we call the expectation of the random variable itself the mean of x. So what we did with the expectation is we took a random variable, and we have now quite a general concept of basically the average of what we would consider the average. So for when you just have the random variable itself or your random number, then this is pretty much exactly what you already know, the mean. But you can also calculate the mean of a function that depends on a random variable now. I always say the function has to be integrable, and this is necessary once for things like here, but also to actually measure the set usually. So only if we can integrate things like the size are actually well defined. So this is why we need the integrable, that the function has to be integrable. And usually we're dealing either with a finite space or with functions that are integrable over all of R. So it's not that much of a restriction actually. Now, with these things, we can also define the variance. And the covariance and the variance of our random variable x is defined as the expectation of x minus its expectation. And all of that squared. So note that this is not the expected length or the square of the expected length or deviation from the mean, but the expected squared deviation from the mean. So basically what we say here, we can imagine that if x was literally a dart that they throw on the plane, we might get something like a cloud of darts here. This might be the expectation of x, and here we have our difference between x and the expectation of x, and we square that here. And basically we look at the mean of the size of those squares, and it gives you an idea of how dispersed the random variable is around its expectation, around its mean. Also the standard deviation. Sigma of x is defined as the square root of the variance of x. So usually what you would read is you have a random variable, or you do some experiment, and it tells you, okay, it has this standard deviation, and the smaller the standard deviation, the smaller the dispersion here. So point cloud that looks like this will have a high standard deviation, while the point cloud looking like this will have a very small standard deviation. And pretty much the smaller the standard deviation, the more precise your measurement. And the covariance of two random variables to random variables x and y is defined as the expectation of the product of deviations. And it gives you an idea of how the change in one of the random variables corresponds to a change at the same time of the other random variable. And we say x and y are uncorrelated exactly if their covariance is 0. And for all here, x and y are random variables. Then there's one final thing that we need for our machine learning, and it is that two random variables are identically and independently distributed. and the two random variables are independently and identically distributed. Exactly if they have the same cumulative distribution function, which gives us the identically, and they must be independently distributed, which means basically if we consider a different random variable of basically first component is x, second component is y, and we can decompose the cumulative distribution function of this new stacked random variable, decompose it into the two cumulative distribution functions of x and y. So why do we need that? Why do we need, or why is it so important that two random variables are identically and independently distributed? When we do observations, when we try to infer something from data, we want to know that what we observe, the different observations, are actually from the same distribution, but basically from the same mechanism. So if one thing is completely unrelated, one measurement is completely unrelated to the other, then it's no use in looking at different observations, right? Then we don't even, then we could not infer anything from them. Also, if they are not independent, if they influence each other, then we have to take care of the fact that one came after another, and we cannot treat them interchangeably. So for most of the machine learning that we do, it is very important that the data that we have is independently and identically distributed, because we want to be able to, first of all, use all the information we have, and second, don't want to treat the measurements that we have in a special order, or give them a special rank, but we want to be able to treat them interchangeably. So maybe one thing, in the beginning we said the probability of a set is equal to its size. So this is pretty much exactly how you already know that, maybe from school, where you counted all the possible ways that the event, where the event takes place, and divide that by the total number of possible events. So when you roll a dice and you ask, what is the probability that the number of eyes is smaller or equal to 3, then you would construct your set A as 1, 2, 3, because it's all the possible values of omega where your event takes place. And omega would be all possible eyes, all possible number of eyes, which would be 1, 2, 3, 4, 5, and 6. And size of A would then be one half of the size of omega, which is then exactly what we define for our probability. So, okay, now having said that, we can erase that whiteboard, and we can go on with probabilistic inference, which tells us how we use all of the things that we've done right now to actually have a very good motivation for the machine learning that we do, like some theoretical underlining some theoretical foundation of the inference that takes place when we calculate a model from the data that we have. So this is called probabilistic inference, and we assume that the data that we have, our different measurements, they are all random variables when we look at them. Like when you look at it theoretically, each measurement could be a little bit different, it's subject to randomness. So we consider it to be a random variable, and we want all the measurements that we have to be, we want them to be identically and independently distributed. So this is an assumption that we have here. In practice, it is not always true, actually. So when you want to predict where somebody went, usually, or where somebody goes next, usually it depends very much on where they are right now. So if somebody is right now in Nepal, the probability that they go to Germany is way smaller than that they will go to India. So if you have different measurements of a person, where the person went, well, they are not independent. But for example, when you want to find out between the relationship between height and weight of people, usually you could expect that this is indeed independent, because the weight of one person usually does not influence the weight of another person, or the relationship between the height and weight of a person has no influence with another person, usually. And the goal that we have here is we want to infer the best possible model from the data. So now, of course, the question is, what is the best model, right? One way of deciding which is the best model, can be maximum likelihood estimation. Now, what does it mean? Let's look at that. Basically, we say we choose the model such that we maximize over all the models that we have to choose from the probability of the data of our observations given the model. That is the idea. So pretty much we say, I think the relationship is the one that gives me the highest probability of seeing what I actually saw. So now let's look at that here. How can we do calculations with that? So the probability of the data given the model is then equal to, because we know that the data is IID, to the probability of x1 given the model times the probability of x2 given the model, and so on. So we can write that as a product. Like this. So basically, this here is the probability of having x1 and at the same time x2, and so on to xn, given the model here. So having this data set pretty much. Now, when we want to find out which model we have, basically, this gives us an optimization problem, right? So it tells us we have to maximize this term with regards to the model. Okay, so that means we have to maximize this product with regards to the model. Now, how can we do that? Usually what you would do is you would find something that you call a parameterization of the model. So you express the model in terms of some parameters. For example, in linear regression, we had several parameters for all the features, multipliers, and we would parameterize the model in terms of those parameters. So after specifying all the parameters, we have exactly specified the linear model. And basically, when you wanted to find out what is the most likely linear regression model, then you would just rephrase this expression with respect to the parameters, to the weights, and you would then maximize that, solve the optimization problem, and you would be done. However, maximizing this product can be quite a tricky thing, because usually when we're maximizing things, we want to work with the derivative, and calculating the derivative of such maybe very large product will be very tricky. So there's a little trick one can apply, because the logarithm is a monotonic function. Applying the logarithm will not change the critical points. So whenever you have something, any function that is monotonically increasing, the logarithm looks like that, by the way. So we can do that because this is, maybe I have to say that as well, this will be something that is greater or equal than 0. So we can apply the logarithm to it. And pretty much after plugging in this expression into the logarithm, we will not have any change in the critical points, because when you say you have a function that has this shape and we want to maximize it, and we apply the logarithm first, what will happen is, so we go to the right, which will mean the logarithm increases, but at some point the logarithm goes down again. Sorry, the function goes down again, which means that the argument that we put into the logarithm will also get smaller again, and the logarithm goes down again. So this way, we can preserve the critical points, but we can do a little trick with our calculations, because the logarithm allows us to write a product, or the logarithm of a product is equal to the sum of the logarithms of all the factors in the product. So we can rewrite this in a little bit different way. We can rephrase the optimization problem like this. And because we know that the probability of the data given the model is equal to the product, we have this is equal to maximizing over the model. The sum of the logarithm of the probability of each data point given the model. So now when you want to differentiate, you can just differentiate each of those terms in the sum, and you can again add it up, which is easier than differentiating a product. Let's do a tiny example with that. Say we want to estimate the probability of a coin flip. And the model would basically correspond to the correspond to the probability of having heads, getting heads. And we parameterize that just with the probability of heads with omega, with theta, sorry. So let's say we do our coin flips and we get h times heads, t times tails. Then the probability of the data given the model is the probability of the data given theta, because we can phrase the model in terms of theta, and that would then be the product of each coin flip, or of the probability of each coin flip given theta, which would then just be theta to the power of heads times 1 minus theta to the power of tails. Okay, so we can then apply the logarithm to that. And it will be h times the logarithm of theta plus t times the logarithm of 1 minus theta. And when we want to maximize that, we can differentiate with respect to theta, and we get h over theta minus t over 1 over theta has this is the derivative, and we want to set it to 0 to find a critical point. And it will turn out that theta has to be equal to h over t plus h. So what does it mean? Basically, the maximum likelihood estimation here for theta gives us exactly what we would maybe naively assume to be the probability. Not the probability, but what we would assume to be the probability of getting heads here, right? We take the number of heads and we divide it by the total number of coin flips. So it's pretty much exactly what we would intuitively do. But now we have a statistic, stochastic interpretation of why we are doing it. And that is quite a cool thing, because it allows us to maybe improve on that idea. It allows us to understand why it works or why it does not work. And it also allows us, or it endows us with a framework to take a probabilistic model and then derive an optimization problem from it. So basically, here we had the stochastic model for it. Then we could derive an optimization problem for inferring the model, and then we solved this optimization model, this optimization problem, and got the answer for our model here. This way is one approach. The maximum likelihood estimation is one approach, but it also has a few drawbacks, right? Because one problem is, even if we know that the probability of heads is equal to 1/2, it's quite easy to get results where we never get heads. Problem with the maximum likelihood estimation. So even when the probability actually is 1/2 and we throw it 3 times, the probability that we think with the MLE that heads the probability would be 0 is 12.5%. And usually you would consider it to be very unlikely, right, that a coin is so lopsided that you always get tails. So maybe it might be of interest to incorporate that prior belief, that knowledge that you have about normal coins. So we have the probabilities for that case here would be 1/12, would be 12.5%. But the MLE for omega would be 0. Yeah. So is there a way to incorporate prior knowledge? And turns out we can do that. We just have to treat our model as a random variable itself. And this idea leads us to what we call the maximum a posteriori estimation, or MAP. And basically, what we do here is we use Bayes' theorem to give us a better understanding. So normally we would say our original question, right, is what is the, we want to maximize the probability of the model given the data we have. But we don't really know how to calculate that conditional probability. So we use Bayes' theorem, and we can rewrite it as the probability of the data given the model. So this is what we already were considering for the MLE, times the probability of the model. This is where our prior knowledge can come into play. And we have to divide it by the probability of the data. So just for nomenclature that we use here, we say the probability of the model given the data is the posterior, say the probability of the data given the model is the likelihood probability of the model, P of M, is the prior. That is the thing that incorporates our prior knowledge. And the probability of the data is what we call the evidence. So when we want to maximize the probability of the model given the data, we can again do a few tricks. Because we know that the probability of the data, the evidence, is the same for every model, right? So this is actually the same thing. It's just maximizing the upper part. So it's enough to maximize likelihood times prior for that, to maximize the posterior. And we can again also apply the same trick as we were applying before, and that is the same thing then as maximizing the logarithm of likelihood times prior. Okay. So what are you guys saying? Should we do an example in the lecture now? Or do you want to do it in the homework? Okay. Okay, then we do the example here too. Okay, so apparently nothing has changed since I was a student. And everybody wants the examples to be calculated in the lecture. Good. So the example that we have here is called ridge regression, which is basically linear regression with something that we call L2 regularization. So basically, we can parameterize the model the same way we did with linear regression. The dependent variable is linear function of our independent variable. And as a prior we choose a normal distribution with respect to the squared length of the weight vector. So basically, the longer the weight vector, the less likely the model is. And for the likelihood, we take just another normal distribution. With a different standard deviation. And here we have the squared distance between what we want, so the y, and our prediction, like the data point y and our prediction. You can think of it like that. We have our data points, let's say 3 data points. We have our linear function, and this here, those lengths, those distances are y minus omega transpose x, y minus our function, and we square them. And the higher the deviation, the higher the distance, the less likely again it is. So after using all the tricks that we discussed, basically we want to maximize the logarithm of the product over the data. Basically, we're now just plugging in, writing likelihood times prior. And because we have here a product of exponential functions, we can use, like, we can all bring it into one exponential function where we are summing what we have as the exponent, where we are summing the exponents. And we can get, we can draw those two factors to the front. We get p times alpha, rho times alpha over 2 pi. And we have the exponential function. We have minus 1/2 times rho squared times the sum over our data points of yi minus omega transpose xi squared. And then we also can add alpha squared omega transpose omega. And now we can apply the logarithm. This is a product again, product of rho times alpha over 2 pi times the exponential of this. And that means we want to maximize the logarithm to alpha plus 2 pi plus or better, minus 1/2 rho squared times the sum yi minus txi squared minus note, I changed that to a minus, that was a mistake, minus alpha squared omega transpose omega and 1/2. Yeah. Oh, this is why there was a mistake. Now, with the parentheses, it works. And do that again here. Delete that. Oh, here we are. So when we want to maximize this, what we can also do, this is a constant. It will not change the minimal point. So we can just drop that. And we can in turn minimize. Also, we can leave out the 1/2. We can minimize rho squared times the sum of the squared deviations plus alpha squared omega transposed omega. We can now rewrite that completely in terms of matrix vector products or in terms of norms. And we can rewrite the norms in terms of matrix vector products. And all the matrices here that we have give us are symmetric positive semi-definite. Therefore, we have a convex problem again. We can just calculate the derivative and set it to 0. And again, we will get some equation. So we differentiate with respect to omega and want that to be 0. And that gives us the following equations. After some rearrangement, you will do that in the homework, no worries. Gives us x transpose x plus alpha over rho squared times the identity matrix times omega equals x transpose y. So this is very similar to the normal equations that we had. However, this time we're adding to x transpose x here multiple of the identity matrix. This changes the optimization problem and the minimal point, of course, as well. So what happens is that when you have one, let's say we add one time the identity matrix, and the eigenvalues might have been very degenerate before. We could have had one eigenvalue. So the eigenvalue of x transpose x, we could have had one eigenvalue of about 1, and the other eigenvalue might have been, let's say, 10 to the power of -4, so 0.0001. And now, when we add one time the identity matrix, every eigenvalue will increase by 1. So now we have eigenvalues 2 and 1. So how does this change the the function that we want to optimize. So before, originally, it might have looked like, or it will have looked like that. It was very degenerate. In one direction, this direction here, there was pretty much no change, or the function is kind of constant. Going this way, a huge change. But after transforming it, after adding one time the identity matrix, what we get is something that is almost circular. And it will have a different optimum. So this is way nicer, way better, way easier to optimize. And small changes in our inputs do not translate into that big of a change anymore, because a little change in the data can move the optimum along the valley very, very easily. There are different priors, by the way, of course. So we could have used not anything, but many different ways, so many different things. You could have come up with something that is very specific to the problem that you are dealing with personally, or for the company that you're working right now. Also, there's a huge variety of priors you can already choose from, where people calculated first the meaning of the prior, so what does it lead to, and second, how it looks like, so the probability density and how it translates into the optimization problem and so on. Also note that because we're multiplying with the prior, in the optimization problem, in the end, we'll always add some term that is only dependent on the model. So no matter which prior you choose, it is some function of the model, and it will translate into some penalty term that you add to the function that wants to adjust the model to the data. And you could have used something that is called the L1 regularization, which instead of adding the L2 norm, adds, or the squared L2 norm, adds the L1 norm. And that favors solutions where more values are equal to 0. So a solution that is more sparse. That way you can actually select features. So features that have very little influence on the performance of the model get set to 0. And this way you can kind of identify which features are the most important for the relationship that you study. One can also show, that is the last thing that I'm telling you about the priors, one can also show that adding a prior in some cases translates to making constraints on omega, on the parameters. And for L2 regularization, for ridge regression, what we get is a constraint to a ball around the origin of a certain size. So we say omega has to be inside of that ball. And we want to minimize that original function. Sorry. Not that nice of a drawing. We want to minimize that while staying in the ball, which might give us something over here, I don't know. However, when you choose L1 regularization, you will get constraints that are this shaped like this diamond. And that means that if the error function slightly prefers one of the axes, you go down in that way as far as you can, and you will go to one of those corners. And going to the corner means going to this corner here means setting this value in omega equal to 0. So in this way, L1 regularization I'll just write that down quickly. L1 norm is basically you sum up the absolute values of the entries, and L1 regularization leads you then to a solution where you favor the corners. Yeah. Okay, so the last thing for today will be the bias variance trade-off. Bias variance trade-off gives us some idea of how good any model that we infer from data can actually get. So because the data is subject to randomness, also the model that we infer will be subject to randomness, and therefore the predictions that we get will be subject to randomness. And the question is, what can we even expect from that, from such a setup? So the question is, how good can we get? And we try to formalize that in the following way. We say we have a process that generates the dependent variable in a functional relationship. So we have the dependent variable is a function of the independent variable plus some noise epsilon. And f of x is the true function, epsilon is the noise, and we say, or we assume, that the expectation of epsilon is equal to 0, and it has a variance of sigma squared. So why do you think do we take the expectation, or why do you assume the expectation to be 0? If it was not 0, well, we could just have changed f accordingly so that the expectation is 0 again. And basically we look at the squared error here now when we ask how good the model is. And we have some data. That we observed. And we inferred a model through some procedure, for example, by solving the normal equations that depends on the data. So M is a function of D. When I give you data, you can calculate the exact model. And that also means that the prediction at some point x that we get is a function of the data, as I said. So we call the prediction at x m of x and d. So basically we evaluate the model at the point x. Now the question is, what is the expected squared deviation? Or in layman's terms, what prediction error do we expect? What squared prediction error do we expect? And the answer is quite simple. You will also do that in the homework in a guided way. We can decompose this term into 3 terms. Into 3 terms like this. So first of all, we have the expectation over the data. So basically, when we take into account all the possibilities of the data and weigh them with the probability, then we get a specific prediction, and we weigh this prediction with the possibility of the data and get this expectation here. And we look at the difference between that and the actual true function f and square that. And this is what we call here the bias. The bias at x of the model, and we add to that here. This is, if you remember, the definition of the variance. Of the model, and here the sigma squared is just the error that we get from the noise that we have. So there are a few things here now to see. First of all, the bias and the variance, they actually are independent of the data, of the actual data that we have. And no matter what we do, so even if we set both to 0, the minimal error would be the noise. So because the best thing that we could do was to extract f of x every time, then the bias would be 0. And because we get the same answer every time, the variance would be 0, but still we would get an error from the noise. Also, for a given prediction accuracy, for a given prediction error, you can kind of choose between increasing the bias and decreasing the variance, or increasing the variance and decreasing the bias. So what that means is you can choose between models. They will have the same performance, but when you get different data, some of your models will always look, or the ones with the high bias will always look kind of the same. You will always get kind of the same answer. However, the ones with a high bias. However, the answer will never really get close to the actual function f. However, if you prefer, on the other hand, if you prefer a model with a high variance, then you can reduce the error to the error towards the actual function. But when you get different data, your models might look different. And one example for that is when you have a huge amount of data and you use a simple linear model. Usually they have a high bias because in reality the connections are rarely linear. And you get a high bias but a very low variance. So when people give you a different data set of the same process, your linear model will kind of look the same. However, if you want to have a model with lower bias that can actually accommodate very complex true functions, like for example a neural network, the problem will be that every time you get different data, your neural network will look very different actually. So you have a high variance but a low bias. And that is something important to keep in mind. You can also further, you can also get further control on the bias and the variance with the priors. So the stronger the prior, or the bigger the penalization of the prior is, the lower is your variance, but the higher is the bias. So you can think about it again in the term of an optimization problem, where this would be the function that we want to optimize. And for one data set, it might look like that, but if you get another data set of the same process, it might be looking like that. And when you now choose the L2 regularization and you choose a very, 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 very weak regularization, which means your weight vector has to be somewhere in that circle, you get a low bias because you can always just pick the one that optimizes this here. However, if you picked a very strong regularization, what you would get for this data set, you would get this weight vector. For this data set, you would get that weight vector. So now you have a high bias because you cannot really reach the true solution, but you have a very low variance. So just to note that again, those were two different models. They are far apart. And those are also two different models, but they are very close to each other. So with regularization, you can also choose how expressive the model is. You can, with stronger regularization, you can increase the bias and decrease variance. One thing where you want to use that is if you want to have a very reliable result. It might not be the best possible result, but it will be very reliable. And if you want that, you would decrease variance as much as possible and just go for the bias, because then you know there is an error, but at least the error will be very predictable because you have a low variance. Also, keep in mind that no matter what you do, no matter how good your model is, if the underlying process has some inherent noise in it, if you have this setup here, then you cannot get better than sigma squared, no matter how good your model is. So even if you have a perfect machine learning system set up, you will still, or in most cases, you will still get problems. Or not problems, I'm sorry. You will still get some errors. And they are totally normal, and nobody could do better. They are inherent. So this is something to keep in mind. I hope that you take a look at the homework for this lecture too. It will guide you through many of the concepts that we've seen today. And it will give you a better insight of what we're doing here and what it means in practice. So thank you very much for coming today. And I hope to see you next week. Have a nice day.